Okay, well, hello everyone. It's 10 a.m. I'm just going to wait a couple of minutes while everyone comes, and then we'll start the presentation. Also, the presentation is recording, so if anyone doesn't want to be recorded, I ask you to keep your screen off. Thank you very much. Okay, I think because we have a tight agenda and we're at the 40 mark, I'll go ahead and start. So thank you, everyone who's joining us, and to those who keep on coming. Welcome to the sixth event of the Soil Community Platform, hosted under Invest in Soil and BIOservicES. For those of us who it's your first time joining us, the Soil Community Platform is a platform developed by BIOservicES and Invest in Soil. It's a platform where we ask and invite everyone who is interested in soil, who works in any type of soil-related projects or initiatives, to join us, to connect with others, to share resources, to publish, to work and collaborate, to host your own events, and to also join these type of events. So today we have a very tight agenda. Today's webinar is called Carbon Farming, Linking Practice and Policy Measurements. And Raul, our coordinator for BIOservicES, will be moderating the session. So I give over the word to you.
Thank you very much, Samuel. So we can start. As you see here, the agenda, we have 5 speakers, very interesting talks about carbon farming with the practices, measurements, and policy updates. So we can start with our first speaker. My pleasure to introduce my colleague, Dr. Alessandra Trinchera from CREA, Italy, presenting some results of her EJP Soil AGROECOSEQ carbon. So, Alessandra, the floor is yours.
Thank you so much, Raul. Nice to meet you today. I share my screen to start my presentation. Do you see the screen?
We see the screen, but not the presentation.
It's shared now. I see the presentation online.
What I see is the website, Soil Community.
Oh, I don't know why, because my presentation is...
Maybe you can...
It's shared. I try again.
Try again.
Try again. So, okay. You see it?
Now, yes.
Now, yes?
Yes, not in
Okay.
presentation mode yet, but we see the presentation.
Oh, it's strange because it is on presentation mode.
Maybe you have two screens, and maybe that's why. Or...
No?
We see the file, but not the presentation mode.
Oh. I try to show you the presentation mode now.
No, not yet.
Probably there is an interference with the other.
Well, I don't know.
With the other screen because
I'm happy to share if you wish.
Okay. Do you prefer I start? Okay. Anyway, because I don't know if the vision is good or not.
It's good.
Anyway, it's good.
Yeah.
Okay. So
Now it's perfect. So go ahead.
not perfect. I don't know how I can solve because I have shared my screen, but is on presentation mode. So I don't know why it is not the same before tested because it's the same. How can I solve?
Samuel, you are muted if you are talking.
Sorry, I think I can. I'm sharing my screen. I think you can see the presentation on my side. It has the same animations. You can just tell me to move the slide.
So I have to start anyway.
Yes.
Yeah, you can tell Samuel to pass the slides if you can see the presentation through the community.
Yes, I do the presentation, but I see in my PC I see the presentation mode. But if I have well understand you see not the presentation mode.
Yeah, Alessandra, we see it well. You can start.
Okay.
No, but we see. But I don't see. But we see it well with Samuel presentation, not with Alessandra. At least from my point of view.
But you can tell me, and I will just tell me when you need me to pass the slide.
Yeah.
Yes. Okay. So I have to tell you how to go on.
Yes.
Okay. Yes. First of all, thank you for giving me the opportunity to present some results from agroecological project, funded in 2022 by the EJP Soil program, led by CREA and involving 8 European and 1 non-European institutions. The second. Sorry, but I have to close my screen because otherwise it's not possible for me to manage. The aim of the project was to understand how the multi-year introduction of agroecological intensification in different European long-term experiments affected the soil organic carbon accumulation, mediated by the plant species in field, the macro, meso, and micro fauna, and the soil bacteria and fungi community. The next one. 7 long-term experiments were selected in a different European pedoclimate context, together with 2 short-term experiments, one of them located in Turkey, as you can see in the slide. In particular, 6 cereals herbaceous cropping systems were considered, 1 fruit orchard, 1 agroforestry, and 1 horticultural cropping system. In each site, 2 agroecological management strategies at increasing level of agroecological intensification, called T1 and T2 in green, were compared to the business as usual management, the T0 in red, the control, which corresponded to the business as usual or the conventional management at each site. They introduced agroecological practices where the no-tillage, the cover crop, mixed cover crop, the organic input, animal or vegetal origin, fungi inoculant. The experimental design consists in 3 treatments, T0, T1, and T2, as mentioned, and the design was based on 4 randomized blocks. Sampling was performed in 2022-23, collecting 3 subsamples per each block, collecting both the soil but also the plant roots at maximum plant demand. The next. agroecological works with 2 complementary evaluation approaches. The first one was based on the measurement of soil health indicators given the ecosystem services provided. The soil organic carbon and the different carbon pools, the soil bacteria and fungi richness and diversity, indexes the mycorrhizal colonization intensity. The second approach, complementary to the previous one, aimed to build descriptive models capable to explain the plant microorganisms interaction that could contribute to soil organic carbon accumulation as affected by those plant functional traits and microbial functional groups that are involved in carbon cycle from literature. The next one. This is the first principal component analysis performed on selected indicators at all the sites. It shows, in particular, a clear separation among the different pedoclimatic areas. The North Mediterranean and the continental cluster associated with the soil organic carbon and carbon pool vectors in the positive semi-plane of component 1. The next animation, okay. The Atlantic nemoral cluster associated with microbial diversity on component 2, and the South Mediterranean and Anatolian cluster associated with fungal richness and root mycorrhization on the negative semi-plane of the component 1. The next. Here we have reported the principal component analysis applied only on soil organic carbon, extractable carbon, and water stable aggregates in each site this time for all the experimental sites. The next. As you can see, the next. As you can see, the T1 and T2 management in green were clearly distinct from the control T0 in red, being the agroecological management mainly associated with the soil organic carbon in the positive half plane of the component 1. These clearly testify the good performance of the tested agroecological practices in agroecological on soil organic carbon accumulation, apart in the Netherlands and in the Denmark systems. We eventually discuss further the reason why. The next one. Here, moving to the measurement of the selected indicators in agroecological, we would underline that the soil organic carbon was significantly increased in specific system under no-tillage and with spontaneous flora herbaceous cover in the Italian organic site, by the mixed cover crop in the French site, and by the organic fertilization with animal manure in the Belgian one. The next. Also in Spain, even if not still significant, we observed an increase increase in these systems of the T1 with respect to the T0. The next one show you the asset of the different indicators that we have collected together. We can argue that the Fabaceae and Poaceae plants promoted the microbial richness, in particular in Italian, in French, and Spanish and Turkish systems. In particular in those management where agroecological practices were introduced. When the cover crop were mixed with Brassicacea species, there was instead an increase of bacteria diversity, which correspond to the lowering of the plant mycorrhization. This happens in the Netherlands systems. That was the same systems where we did not observe the increase of organic carbon. The next one. We also observed that in no-till systems, the spontaneous root mycorrhizal infection of plant species in field increase, in particular in Italian, Lithuanian, and Spanish site. As expected, also high correlation between the soil organic carbon and the water stable aggregates was found, which confirms, as a matter of fact, the fact that the soil organic matter act as a binding agent for the soil particles, as also reported in literature. The next. Finally, it was also observed that more than the soil-dominant bacteria and fungi group are the rare bacteria and fungi taxa that are mostly able to differentiate the agroecological management from the control. And we can say that they could be considered as useful benchmark for assessing the soil quality. The next. Here, the PLSM model, that is a descriptive model, where we evaluated the relationship between plant functional trait, microbial group, and soil organic accumulation. The redundancy analysis highlighted that the model is able to explain more than 54% of the soil organic carbon variability in the study system. This model worked with the whole data related to all the experimental sites analyzed in agroecological. The next. The selected plant functional traits here reported in green did not have a direct effect on soil organic carbon. As you can see, the hexagon in green is connected to the hexagon in blue that correspond to the soil organic carbon pool, but there is no significant effect. But the next. The plant trait significantly reduced the relative abundance of anaerobic bacteria, MP cyanobacteria, litter and dung decomposers, and mycorrhizal fungi. That means the functional group in yellow, where a significant effect, as reported on the arrows, are found. The next. In turns, the different fungi and bacteria group selected negatively influenced the soil organic carbon accumulation. So we had that functional group affect some negatively specific group, here reported, that are decomposers. So those groups that mineralize organic matter in the soil. So the next, since they negatively influence the soil organic carbon accumulation, at the end, we can say that the selected plant functional traits, that means the specific leaf area, the grass trait, and the perennial traits, lowered those microbial decomposers in soil, bacteria and fungi, which lower the SOC, thus indirectly they support these plant functional traits support the soil organic carbon accumulation. The next one and the last one, these are only just some of the results achieved in the AgroEcoseqC project. We would anyway suggest some recommendation coming from the results. Select carefully the plant species to be used as cover crop in function of the expected ecosystem services, considering their ability to shape the soil microbiota. Also by selecting the rare microbial fungal functional group that are capable to sustain the soil organic carbon accumulation. Promote the no-till and or minimum tillage, as well as the application also of organic fertilization, because they can allow to increase the soil organic carbon up to 20% in specific environment, for example, in Mediterranean semi-arid cropping systems. We see this effect in AgroEcoseqC. Introduce tailored agroecological practices to address the multifaceted context-specific European environmental challenges that are, of course, different in the different context. Is the next. And the next one. I have listed some articles already published that you can consult if you are interested in detail of what I have presented. If you need further information, you can contact me or my colleagues to go in depth with. And thank you again for this opportunity given to me and to all the group that participated to AgroEcoseqC. So thank you.
Thank you very much, Alessandra. So, okay, we move to next speaker and we will have our discussion at the end of the session. So we move to next, who is Dr. Emanuele Lugato from the Joint Research Centers, talking about the insights in CRCF-based methodologies. So go ahead, Emanuele.
Yeah, sure. Hello, everybody. I hope you can hear me and see the presentation in full.
Yes, we see the presentation and we hear you.
Oh, perfect. Okay, thank you a lot for inviting me. So in this presentation, I will give a flavor of how, let's say, we use different data set and modeling approaches for developing the baseline under the CRCF, the carbon farming certification. Yeah, the time is very limited, so I can only give you, let's say, a quick overview, but I hope you get the sense of my presentation. And I will focus in particular in the agricultural methodology, which comprise mineral soils and agroforestry. But in particular, we focus on mineral soils because we know somewhat how difficult it is in real field condition to detect soil organic carbon changes to the inert variability of the soil organic carbon distribution and the interannual variability of the carbon cycle. So in the short term, we know that there is many practices, these are not an exhaustive list, that can increase the soil organic carbon, changing the soils or also reduce emission. But of course, it's very difficult to detect small changes, and for this we need really data on farm activity, ancillary data, and we need also proper tools that can somewhat allow to predict the soil changes in a cost-effective way. This is very important for the CRCF, which aims to create very credit with high values, and for this we need to have a robust and accurate estimation of soil organic carbon changes. But of course, this has some cost, so we really need to do in a cost-effective way, particularly using also some modeling approaches. And in fact, according to the regulation for what concerns the soil organic carbon, let's say lower emission factors, lower tier approach are let's say not allowed, but only tier 3 modeling, so advanced modeling will be somewhat allowed, including also, of course, measure. And an important, let's say, aspect of the quantification is certainly the baseline, because it's given our additionality to the carbon farming activity. As you can see from the equation, only the if you want carbon removal, the carbon that is removed more than the baseline can be accredited, or the lower emission compared to the baseline. And there are different types of baseline that mainly project specific, so defined at the level of field condition, and in somewhat representing what is the current management without the introduction of the carbon farming activity. But the regulation also introduced the concept of standardized baseline, meaning that we look more at the region, at the similar environmental condition and the performance emission removal that are so in this region, which has somewhat similar soil, similar climate, and also similar socioeconomic circumstances. This is more a kind of a, let's say regional baseline. And both can be anyway static, so we can provide a fixed rate of change at the beginning of the project, because the baseline at the end it's an emission or removal rate is a carbon flux to be compared with the let's say sequestration rates of the measure, or can be also dynamic, so that can be updating time, take into account of the change in the climate conditions, or also on some management in the baseline. But this of course require the two, let's say, approaches require a different complexity, and this is what we explore in a project at the GRC called CRL, Carbon Removal Land, in collaboration with DG Clima, where we tested a different data stream, different data set, pan-European data set coming from Lucas soils or from modeling, and creating, as I'll show you later, a kind of fixed baseline, or also using, let's say, more advanced process-based model integrated with remote sensing to work really at parcel scale, and creating, let's say, having a tools that can work, can provide either a project specific or a standardized baseline. And yeah, just to give you an overview of what we have done, when we talk about when we use, let's say, this kind of large scale data set like Lucas, that, as you know, it's a big soil sampling conducted now since 2009, and we have data also for 2015, 2018, and 2022 that are not yet available. And with the Lucas data, we can basically calculate in the repeated point the difference in soil organic carbon between 2018 and 2009. We have about 5,000 points, repeated points, and we can somewhat try to predict this difference, this change of soil organic carbon using a typical machine learning model. In this case, we use a GAN, and with the use of other covariates which are related to the carbon cycling, like the soil texture, pH, the land cover, etc. And the idea was to simply have a train model that can be then upscaled continuously in space using very high resolution data set, including also the new vegetation land characteristics. There are 10 meters layer provided by the land monitoring system by Copernicus. So the idea is that we have the data, we have the change, we have a machine learning that try to predict these changes using other covariates, and we can then from 5,000 points to get continuous spatial prediction. And also we also have the GRC, some big modeling framework using a process-based model, an ecosystem model that simulates the carbon and the nitrogen cycle. And we repeated this exercise, but using the model input and output. So creating, in this case, what is a model emulator or a meta model. So a way to reproduce the model results with a set of covariates without running a model, but passing this synthetic data set to, again, a machine learning, a random forest model, and making, again, prediction at a much higher resolution. So these two approaches, somewhat, one is allowed to create two scalable models, one which has the information of the data, one has the information of the process, and they can create a model ensemble to then provide the static baseline. So essentially producing some maps of soil organic carbon changes at a high resolution. Then also with the synthetic data, with the data from the model.
Oh, I think your microphone might be muted, Emanuele.
Something happened.
Yeah, I think we lost Emanuele.
Oh no, Emanuele, can you hear us?
Maybe we lost him. Not connected anymore. Yes, connection lost when I click on Emanuele. Let's wait if he connects soon.
Perhaps we could move on to Chiara for now.
We can move, yes, because I don't see him. Maybe we can move and let him
I'll send him an email.
restart after Chiara. Yeah. So, well, sorry for this. We don't know what happened. So we will move to next speaker, Dr. Chiara De Notari from the CMCC, the Mediterranean Center for Climate Change, and also represented in the Soil and BIOservicES projects, talking about certification of soil health benefits. So, Chiara.
Yeah, thank you, Raul. You should be.
We see the presentation and we hear you.
Yeah. So thank you for the introduction. I'm part of both projects in the Soil and BIOservicES, and well, my presentation connects quite well with what Emanuele was presenting, because he was focusing on the certification of net carbon removals and soil emission reductions, and I will look more into how we could integrate soil health certification within the carbon farming certification framework. How is soil health included within the carbon farming certification framework? Carbon farming activities are required to generate co-benefits. So there are some mandatory co-benefits that have to be generated, and in particular for the protection and restoration of biodiversity and ecosystems, including soil health. On top of these mandatory co-benefits, farmers or land managers in general should be incentivized to go beyond minimum sustainability requirements. But guidelines on how to certify these co-benefits should be provided. Just to give you some more insights on the regulation and how the methodologies are being shaped at the moment, mandatory co-benefits will probably be certified with an action-based approach that promotes synergies with other policies. The idea for now is to leave the operators the choice to demonstrate these mandatory co-benefits based on peer-reviewed scientific literature or aligning with measures that are consistent with the nature restoration regulation or in synergy with the Habitats and Birds Directive or for agroforestry, aligning with recommendations from the European guidelines for biodiversity-friendly afforestation, reforestation, and tree planting. So mandatory co-benefits will be deemed as being complied with simply by proving that some actions are being undertaken. For voluntary co-benefits, it's a slightly different approach because voluntary co-benefits should generate a market premium for the certified units. So they are voluntary, and if operators can prove that they are going beyond the minimum, they should receive a market premium. There are some examples of these possible co-benefits that include climate mitigation, improved water infiltration, pollution prevention, and also improvement in biodiversity beyond the minimum requirements. But importantly, there will not be common methodologies on how to certify these voluntary co-benefits, and operators will be able to use their own approaches. A few things to note is that the list of co-benefits is open, so there will not be a fixed list of things that operators can choose from, they can decide. These co-benefits will not be converted into units, but it's just information that is provided in the certificate of compliance. And this is somehow a pilot phase, like the phase that will start in 2026 is somehow a pilot phase, and the lessons learned from this phase will be used for the later updates of the regulation and maybe also for the development of nature credits. And so, since no common methodologies are being developed, what we would like to do is to propose some approaches that operators could use for the certification of soil health. And the idea is to stay within this hybrid approach where an action-based approach is used for the mandatory co-benefits and a result-based approach is used for voluntary co-benefits. In a result-based approach, results are measured using indicators. These indicators should be intuitive, sensitive, and accepted. And also, the certification of these voluntary co-benefits should not be an extra burden for farmers, because otherwise it would not be convenient. And since we are in the context of the carbon farming removal, carbon is one of the things that will be monitored. So soil organic carbon-based indicators could be a cost-effective choice. Within the Soil Monitoring Directive, one interesting indicator is the SOC to clay index. But this index has been criticized by recent scientific literature, and an alternative indicator has been proposed, and that's the observed to typical SOC index. The reason why the SOC to clay index was criticized was because it was shown to be biased by the clay content. And using data from soil agricultural sites, we tested this, and indeed the SOC to clay index was biased by the clay content. So the sites with a low clay content were classified as being in very good conditions, and it decreased the soil quality decreased with the higher clay content. On the other hand, the OT-SOC, so the observed to expected SOC ratio, was not as biased, so the distribution was not linked to the clay content as the previous one. And then why using this soil organic carbon indexes could be a cost-effective choice, because they can be used as a proxy for soil structural quality. And we checked if this was true, again, using data from Invest Soil agricultural sites. And what we could see was that indeed the OT-SOC index was well related with bulk density and porosity. So sites with a lower bulk density were classified as being with a very high OT-SOC index, and on the other hand, with a high porosity. So it seems like it's a good indicator for soil structural quality. But on the other hand, soil structural quality does not represent soil health in general, because sites with a high OT-SOC ratio can still have excess nutrients or heavy metal contamination. So a multi-indicator framework should be used. And so if the OT-SOC index can be used as a proxy for soil structural quality, that's a starting point. And soil structural quality is related to flood regulation and water storage, which is one of the co-benefits that can be certified and valued by farmers especially. I will not go into the details of how the OT-SOC index is calculated, because that's not our work. It's from FINE et al. So it's work that has been conducted in another context. But adopting their approach, we classified our agricultural sites. Here it's LH7, LL1, and L2. It's Lighthouse 7, Living Lab 1 and 2. That doesn't matter, but you should know that these three sites are distributed in different biogeographical regions. So we had an Atlantic site, Mediterranean, and a continental with different soil texture. And then we have the observed soil organic carbon. This observed soil organic carbon was put in relation to the typical soil organic carbon, so what is typically observed under these conditions. And what we then did was to compare for each of the sites, compare treatments where carbon farming practices were implemented versus the control where no carbon farming practice was implemented. And what we could see was that in general, biodynamic and regenerative treatments managed to increase the OT-SOC ratio, so had a positive effect on soil structural quality that is related to flood regulation and water storage. But then, as I said, that's not the full, that doesn't give us the full picture. So other indicators, and in particular indicators of nutrient availability, could be relevant to monitor because they relate with nutrient cycling. So we looked at total nitrogen and extractable phosphorus in the same agricultural sites. And what we could see was that total nitrogen increased again in treatments where higher input of organic matter was provided. So organic, biodynamic, and regenerative treatments, while we had some sites where treatments were mostly related to tillage. In those cases, that didn't really have an effect on this. But then again, is a higher nitrogen and phosphorus availability an indicator of increased soil fertility or an increased risk of losses? Looking at extractable phosphorus, two of our sites, so the Atlantic and the Continental, were above 50 milligrams of phosphorus, extractable phosphorus per kilogram of soil, which is above the threshold for excess phosphorus. So in these cases, maybe having more nutrients is not a good thing. So these type of indicators should be put in a broader context. And then another key aspect that is also quite meaningful for farmers is biodiversity, but soil biodiversity is quite complex to measure with simple and cheap indicators that are also easy to understand. In InvestSoil, we looked at several indicators, but for simplicity, we focused here on total PLFAs, which simply indicates the total microbial biomass. So it provides partial information. But in this case, again, treatments where a higher input of organic matter was provided had a higher total PLFA content, and also treatments with reduced tillage had a tendency for higher soil microbial biomass. But in this specific issue, BIOservicES is focusing on soil biodiversity and is working to develop some proxy indicators that might be easier to measure and also to be communicated and understood by farmers. So putting this together, if we had to do an overall assessment of soil quality in the soil agricultural sites, again, we had 3 biogeographic regions with different types of carbon farming activities that included addition of organic amendments, reduced tillage, and regenerative practices in general. We could see that the Atlantic site had a positive effect on all the aspects that we investigated, with a question mark on nutrients availability, because yes, there was a higher nutrients availability, but is that good or bad? Then we had one of the Mediterranean sites where no effect was observed of reduced tillage and sod seeding, but it should be noted that in this specific case, all the treatments were classified as high according to the OT-SOC index, so maybe simply there was little room for improvement here. And in the other cases, in general, soil structural quality and microbial biomass were improved by carbon farming activities. And since this type of co-benefits, again, should not be really converted into a unit, but simply communicated in the context of the carbon farming certification framework, this is the way maybe, this could be a way in which soil health could be communicated. But just to put forward some recommendations, so soil health indicators should be embedded in certification methodologies with a focus on a multi-indicator approach, combining physical, chemical, and biological metrics. But the indicators chosen should be intuitive for farmers and policymakers, because if it's voluntary and no common guidelines will be provided, then it should be easy or doable for the operators to understand what they are doing. Then alignment with the soil monitoring directive would also be really good, so that the indicators that will be monitored through the directive could also provide a baseline and some benchmarks to have a more robust assessment of soil health. And this is linked to the next point, that is to develop context-specific reference values for key indicators, because this would be good also for operators to understand how they are performing and where there could be room for improvement. And then again, synergies with other policies such as the CAP and the Nature Restoration Regulation. And regarding nutrient management, nitrogen and phosphorus indicators should be linked to management practices, because, for example, higher nutrient availability in the soil could mean improved soil fertility if the nutrients are retained in the soil. So if the soil has a continuous cover, for example, with cover crops, then that's a benefit. But if the soil is left bare, then that might be related to an increased risk of losses. And then, capacity building and knowledge sharing, and that's what we are also doing here. So exchange between projects, but also with stakeholders in general. And that's it from my side.
Okay, thank you very much, Chiara. So I think that Emanuele Lugato, you are already here. You're back.
Yeah, I'm back.
Something happened.
Sorry for that.
No problem.
But the funny part is that I went to the end of the presentation.
So you kept
and
talking. Sorry.
I realized that nobody was listening to me.
So you can restart. I can tell you where you.
Yeah.
Where we lost you.
Okay. I will share again. Yeah. Sorry.
So we were here.
Okay. Just a second. Okay.
Okay, you talked about this.
Okay.
And we lost you here.
Okay. Yeah, okay. So these were two, let's say, approaches that I explained before, where data, real data, measurement data, were used to train statistical models and machine learning models and to make a prediction in space. And we also did it with a synthetic data set come from a large-scale modeling with a process-based model simulating carbon nitrogen cycle. So we built a kind of model emulator in a way that we can have to train statistical models that are scalable and can be applied anywhere in Europe with high resolution data set and providing a kind of model ensemble of a static baseline, because we somewhat wanted to predict the soil organic carbon change in this time frame. And but with the synthetic data, with the modeling data, since we have a change of soil organic carbon in times, and we have also simulated productivity, we have the climatic data, and we have also other fixed predictor. We can also feed a deep learning model and try to predict the behavior in times, to reproduce the behavior in times of the soil organic carbon changes. And again, we can obtain, once the model is trained, a scalable models that can be applied by any user with his own time series of primary productivity or meteorological data. So the advantage of course, of training this kind of models, that they can be somewhat applied using the same set of covariates, time series of covariates, without running a very complex process-based model that required a lot of competence and also IT capacity. And I would like to say that we somewhat tested the different approaches that we elaborated, the different model approaches in area across the Europe, also in collaboration with some soil mission project like MRV and MRV4SOC. And very quickly, when we predict the soil organic carbon changes from 2018-2009, we obtain slightly different values using different models. This is really common because any model has its own, let's say, data input, its own assumption, its own structure, and it's very difficult in general to have the same number when we try to predict the soil organic carbon in a region. In general, the numbers are very slow because it's the change of stock in the topsoils for 10 years. So you have to divide by 10 to have the annual rate. But in general, we think that let's say a good approach is always to work with a modeling ensemble. So to get, for instance, the average of many estimation, and this is also show by literature that model ensemble can really provide less bias estimate, because in general it's very difficult to know which one is the best, or which prediction is, let's say, the most accurate. So before I show you, if you want, a kind of a way where we use some large-scale data measured data from the Lucas sampling and some modeling data to create some scalable model and then making a prediction in space. Here I wanted to show you a different methods where we try to directly simulate the soil organic carbon at a very high resolution using remote sensing data that can, let's say, be useful to monitor the farm activity, but also to predict the plant productivity in general, in this case with a typical light use efficiency model, which convert, let's say, the remote sensing signal in productivity, also using the radiation and other weather parameter. And this approach allowed to estimate the productivity, but also to feed a carbon model, which in this case is the MEMS model, a carbon model that simulate soil fraction that are measurable, like the mineral associated and the particulate organic carbon. And we built this framework, and we are still calibrating and testing, but this is show the potential of this framework, as we can estimate, calculate the productivity of a grassland parcel, for instance, daily, and we see also at very high resolution, because we use Sentinel-2, and so we can see pixel of 10 meters, we can see the intrafield variability. And of course, the part of the productivity can be transferred to the MEMS models and simulated the carbon changes, and you see that in this case the changes in organic carbon from 2000, I don't remember, 21 to 2017. Okay, and we see also how the change is distributed into mineral associated and particulate or organic carbon. So one, of course, is more stable, and then the POM is more, let's say, subjected to the changes. And this is a very promising approach, because it allows to simulate every single field, so having a kind of project-specific, if you want, baseline, but at the same time, if you consider many fields in a region with similar characteristics, we can simulate, we can estimate the standardized baseline. So it's a very unifying approach. So I'm going to the conclusion, saying that, of course, the CRCF wants to create a reliable voluntary carbon market. And for this, we need really to have a good estimate of soil organic carbon changes, which is always a challenge, and because soil organic carbon is characterized by high variability and low magnitude of changes, and so we really need the cost-effective MRV system. Otherwise, the cost of the certification can kill all the whole market. And to do so, of course, we need data. We need to improve the knowledge on biochemical processes. We see, for instance, before, how important is the microbial component, but how it's difficult to then insert into in a mechanism, in the mechanism of the process-based model. But we have also a new possibility offered by, for instance, assimilating data like the remote sensing. And the way forward is always to, of course, collaborate to do model intercomparison, to understanding, and let's say, which is the best way forward, and of course, also producing ensemble of modeling that are likely, let's say, a best solution to provide the less bias estimate. And also, we need to making a lot of outreach and to somewhat give available the tools that we created in order that anybody can benefit from the work done. So, and this is my last slide, and yeah, thank you a lot.
Thank you very much, Emanuele. You finished.
Oh, we did it.
You did it. You were not alone. Thank you.
Thank you.
Okay, I remember you that if you have any question for the speakers, you can use the chat to post any questions, and we can forward the questions to speakers at the end, or you can wait until the end when we open the discussion session. But you can, if you have some questions, you can already start asking them on the chat. So we move to next speaker. It is Dr. Bertrand Guenet from the CNRS, representing MRV4SOC, talking about modeling and upscaling uncertainties and implications. So you can start presenting if you manage to do that.
I will share my screen. Put it full screen. Can you see my screen?
We can see your screen perfectly.
Okay.
So you can start. Thank you.
Okay, thank you. So thank you very much for the invitations and for giving me the opportunity to presenting some part of the work that we are developing within the MRV4SOC project. And in particular, today I will talk about the way we use models, and we try to propagate some uncertainties in those models, and what are the implications that we have when we want to upscale our approach. So very first, well, I don't know, the quality of the slide might not be super good, but okay, anyway, just to mention that this is a plot coming from a paper by Roberta Farina, where basically it shows that you have like a couple of scatter plots for different models. So you compare observations and models output. And what we can see here is that in this multi-model exercise, basically when the model they are well calibrated and they are well informed by the boundary conditions they need, the process-based model are a powerful tool to predict the soil organic carbon. But this being said, if we want to use those process-based model to upscale, we need if we want to calibrate, then it's a bit more complex for a couple of reasons. One of them is that most of the time when you want to upscale to larger regions, you won't have all the data you need. And also, basically, the parameters, they can be also specialized. So you may need different set of parameters for different locations. So let's say that the calibration part is a tricky part, but I won't talk much on this in this presentation. I will mostly talk about the robustness of the model depending on their boundary conditions. So basically, the soil models, the process-based soil models, they can be robust, but only if their boundary conditions are robust. And what I mean by boundary condition is basically all the inputs that the model needs to run. So basically, that will be like the meteorological, so temperature, it can be precipitation for soil models, it can be soil moisture for other models, and so on. The carbon inputs, obviously, that are coming from the plants, the soil texture, etc., etc. So the different models have different boundary conditions, but if those boundary conditions are not robust, then the model cannot be robust. Basically, this is the simple sentence like sheet in, sheet out. This is what's going on. So if you want to use those process-based models to upscale, then the upscaling quality will also depend quite a lot on the quality of your boundary conditions. something which is important to note is that when you upscale, most of the time you will use maps or you will products that are not direct observations. They are upscale also. Their product they are also upscale at some point, and those products they came with uncertainties. And it's a very important question to know how those uncertainties will affect the model predictions, and that will be the question I will try to answer during this presentation. Here in this modeling exercise I'm showing you is we use the ROTC model. So the ROTC model is a very classical model. It has been developed in the 19th by Coleman and Jenkinson. It's basically divides the soil organic matter in different pools. And the decomposition is controlled by the equations here on the slide, which is the first order kinetic equations. Basically, it means that the decomposition depends on the quantity of carbon you have in a given pool, and you multiply this quantity by the decomposition parameters, which is itself controlled by some rate modifiers depending on temperature, moisture, soil cover, and so on and so on. So that's the model we are using in this exercise, but I will try to have the presentation not too much model dependent. Then, so the inputs that we need for the ROTC model, they are basically the carbon inputs that come from the plants or from organic fertilizers. In our case, we used estimation based on satellite observation or national statistics. It needs climate information, so precipitation, potential evapotranspiration, air temperature, and here we will use the climate from the ERA5 lens product, which is one of the most up-to-date climate products for the land surfaces, and the clay content mostly it's coming from national maps. Then, okay, how we estimate uncertainty propagation. So here there is a very key point that is important to note, is that what we are doing in this exercise is not like a full uncertainty propagation analysis. We are not testing the uncertainty propagation from the parameter or from the model structures. We are specifically testing how the uncertainties from the boundary condition product we use to force the model, how those uncertainties they propagate into the model predictions. Okay, so that's something which is important to have in mind. When you want to do this kind of exercise, there is a lot of methods available in the literature. I won't do a literature review on that, but it's a full research area. In our case, we decided to go for a Monte Carlo approach. Because first, it's a very classical approach. And the basic is that you compute the result of the model a lot of time with input values that are sampled in the distributions of those input value. I will go back into that a bit more later. And also, technically, it's really easy to implement because I quote this sentence from a book chapter from Gerhard Övling, which basically it's no more than adding an extra loop around an existing model. So it's not difficult to implement technically. So basically, what do we have? So here we have the carbon inputs. Here you see that you have a probability distribution of the values, and what we do is we do a random sampling a large number of times into these areas of probability distributions, and we run the model n time. And based on that, we have an average which is given by the model, but we also have a confidence interval that give us how this uncertainty in the carbon input here, for instance, is affecting the projection of soil organic carbon dynamics by the models, and you can calculate these confidence intervals here in that case. And when you do this for all the different boundary conditions, so you can have the value for all of them, but then you can also run the same protocols, but you fix the clay. And so the difference between this and this is the effect of the clay. You do the same for temperature, you do the same for inputs, and so on, which makes that at the end, you can estimate which boundary conditions is the most important contributors to the total uncertainty. So just to give a bit of methods here also, but basically we did 500 iterations. It's based on, we chose these numbers based on the work of Noel et al. I can enter later on the details if you want, if you have some questions. We run the model until equilibrium, and then we propagate the uncertainties, and we consider that the difference are significant if there is no overlaps between the 95% confidence intervals. And then, as I was explaining, to estimate the contribution of each single boundary conditions, we propagate the uncertainty of all the boundary conditions except the boundary condition we are interested in. So also what we did is that we run some scenarios. So we run some scenarios that we called carbon farming scenarios. I think here it's also important to have in mind that in this exercise, what is actually a carbon farming scenarios is just an increase of the carbon inputs. We do not consider all the change that we may have on the porosity or the change that we may have on the biodiversity and so on and so on. So it's like a simplified way to see what carbon farming is, obviously, but in our situation, it goes only through carbon inputs. We have three scenarios. We have plus 20%, plus 50%, of plus 150% of inputs, plus a control. Those scenarios, they are based on previous literatures. And we combine also with a temperature increase scenario of plus 2.5 degrees, which corresponds to the result of basically what we expect for the SSP 5.8.5 scenario from the IPCC in Europe for roughly 2050. So what I will show you is that in the projects, we have a couple of different experimental sites, but I won't show you all the details because time is running. But I will mostly focus on one of the sites, which is the Lonze site in Belgium. This is a very classical crop site, as you can see in Belgium or in northern France or in this part of Europe. So basically what you have here is the delta soil organic carbon. So it's the change of soil organic carbon predicted by the model since the beginning of the simulation. So that's why it go around zero. It's not the soil organic carbon stocks itself, is the difference between the soil organic carbon stocks at a given time and the soil organic carbon stocks we have at the beginning of the simulations. And we have here the control, the temporal dynamic of the control. And we have the blue line here is the average, and the bluish area is the confidence interval. So this is for the control. Then if we plot the scenario with plus 20% increase, we can see that the two confidence intervals, they always overlap, which means that with this kind of models, we can't really say that we observed a significant increase of soil organic carbon when we increase the input by 20%, because we have this overlap between the confidence intervals. Then if we increase by 50%, then here we can see that indeed, after a couple of years, we have the two confidence intervals between the control, the blue one, and the plus 50% increase, the green one. They do not overlap anymore. And so here we can say, okay, despite the uncertainties that from the boundary condition that propagates in the model's output, we detect a significant change in using the model. And obviously, if we go for even a bigger increase, then the difference are significant much earlier in the simulation. And now, if we combine this approach with the 2.5 degree scenarios, what we can see here is that if we increase the temperature in the model, then we have a significant decrease of soil organic carbon if we keep the carbon inputs as they are. If you increase the temperature and you also increase the inputs, then basically we have somehow the same result here. We can't say that the difference is significant because the two confidence interval, they overlap. But if you increase by 50% and you increase the temperature, basically you're going back to your control. So what does it mean here? I think it's an important result because it means that if you trust your model, if the temperature increase, it may lead to a bigger decomposition, so a loss of soil organic carbon. And if you do not compensate for this loss by an increase in carbon input, at the end your system will lose carbon and will emit carbon to the atmosphere. And at the end, obviously, if we increase the carbon by a very large fractions, we are still storing carbon in the systems. And now, if we look at the relative contributions, I think something which is interesting here is that you can see that the most important contributor of this uncertainty is actually the uncertainty on the precipitations. This is something that is relatively straightforward to understood if you have the chance to discuss with a meteorologist, because basically what they told you is that the most difficult part to predict in the meteorological data are the precipitations. And indeed, the uncertainty in the ERA5 lane product for the precipitation is relatively high. What does it imply? It means that if you are able to reduce your uncertainty on the precipitations, you will, at the end, reduce the uncertainty on the soil organic carbon, because this is the main contributor. So basically, the take-home message of my presentation will be that we can use a process-based model. It can be an option to upscale from site observation to landscape scale, and you can use some regional products to inform this model, but you have to take into account that those in regional product that you use to inform your model, that you use like boundary condition of your model, they are also coming with uncertainties, and so you can't trust the model. The model mean you need to understand how this affects your model projections. I think it's also important to have in mind that those process-based models, even though they are useful tools, they are nothing more than a tool, because they are just a simplification of the reality, and not all the carbon farming effects are represented, as I was explaining. But at the end, their quality depends quite a lot on the quality of the data. Here in our situation, in the site I showed you, the most important uncertainty, the most important contributor of the uncertainty was the precipitation and also the clay, which means that if you're able to have better products for these two main drivers, at the end of the day, you will reduce quite significantly your uncertainty on your model productions. Just to let you know that in the MRV4SOC project, this approach is applied to other experimental sites. But basically, we have the same kind of results for all the experimental sites, but we still need to keep going with all the others to be sure that this take-home message is valid as a European case. So I think that's all for me. Thank you very much for your attention. And yeah, I'll be happy to discuss later on if needed.
Okay, thank you very much, Bertrand. So we move to our final speaker. My pleasure to introduce Dr. Tristano Bacchetti from Site Innova, presenting results from Credible project about scaling carbon farming. So Tristano, the floor is yours.
Okay, please confirm that you see it well, full screen?
Yes, perfect.
Okay. So first of all, thank you for giving me the opportunity to present. I have to say I have a bit of a cough, so hopefully I'll manage. And if I fall off the chair while I'm speaking, just bear with me for a second. So I'm gonna present, let's say, Credible. And Credible is a coordination and support action. So there will not be in this presentation and in the project, there hasn't been a lot of hard science and innovation. So as a presentation will feel a little bit different from the one that preceded me. But hopefully it would feel more like an overview of the many challenges and sometimes opportunities that we still face in developing a credible carbon farming sector. The project itself, I mean, you can see here the structure, the organization that are participating. The project itself is about to finish, so in May will be the end of the project. So we are closing. Okay, so the main the key elements, let's say, to build a carbon farming system can be summarized in three things, like practices, MRV standards. So practices are obviously the action that we wish to promote, those actions that have or we expect, we hope, they have a climate impact. So it's the change that we want to generate. The MRV we discussed, everybody here now I think it's understand the issue, the importance of robust monitoring and verification, and obviously the standards, let's say the policy, the structure, how you certify the workflow that enables the system to exist. And these three elements are kind of being the subject of three different work packages within the project. So we have looked in all this direction, which also add a little bit of complexity from my side when presenting results, because by looking at everything, then it's very difficult to get into something detailed that often scientists prefer, and it would in the 10 minutes that I have, it will remain like a broad overview. But anyway, in order to, let's say, contribute to build credibility in these three directions, the Credible operated basically three main processes. These are focus groups, yearly public consultation, and the European carbon farming. So the focus group were basically led from the beginning by credible partners. We have started focusing on, let's say, 11 questions that we identified 3-4 years ago and writing the proposal. And basically, each focus group, we have invited experts. So it is the mechanism by which our project has tried to sum up all the knowledge that exists in the scientific community, but also in other stakeholders, and bring this knowledge to the Commission while the Commission was developing the carbon removal and carbon farming framework. And so we have had this like focus group, and let's say an average of 10 people per focus group participating. So it was already kind of a network projects existing that we convey towards the Commission. These focus group they went through yearly cycles of exploring the question that we decided to focus on. And try to really come up with concrete recommendations for the Commission. Those recommendations, the focus and the timeline was to basically share them at the summit, also contributing to give visibility to those, but also collect further inputs from stakeholders and colleagues, and then captured in what we launched as a public consultation. And so we have done this cycle already twice. Now in the last year, we will probably focus on the summit. The summit, it became and will be the legacy of the project for sure, because we exceeded our expectation every time. So we did 2 summits so far. The first one, for example, we expected, we booked a space for 300 or 350 people, and that went overbooked in days. And we had to open an online version, and that also went overbooked. So next year we doubled in size and also overbooked. So there is this really demonstrates that there is a lot of interest in carbon farming, and it's great to have a space where stakeholders can meet and discuss and develop, really concrete recommendation to overcome these challenges that we have. And briefly, some key takeaways from this summits are highlighted here. So from the first summit, what really felt like a scientific consensus was that it was for carbon farming as a business model, as a mechanism to create change. It was really important not to focus just on carbon, because we have, apart from the technicalities that is actually difficult to measure, to have an impact, but in general, many other elements, such as the fact that carbon farming as a term does not really appeal to the farming sector. So it's really important to be impactful, to look broader and make sure that with carbon, we also look at environmental benefits, social benefits. That's how we develop a system that works, because the science may be working. You identify the good practice in a specific context that does increase carbon content, but then it's a business model. You have to really promote change, and that happens only if you look at of all elements together in a more holistic way. So this was very key from the beginning. We have tried to communicate this clearly to the Commission in the development of the certification framework. Obviously, in the second year of the summit, we had more session, more recommendation, and we come up with these 7, let's say, key takeaways that it is still important. These are challenges that are important to, it's the stakeholder that can work out these challenges can really generate or contribute to generate a better carbon farming system. So this issue briefly are, and I know that most of you follow the topics, so you probably have heard them all, and some have been mentioned by my predecessors. So it's nothing new, but it's important to keep them in mind. As scientists, we try to become focused on something, and it's good sometimes to have a bit of an overview to understand where and how we can contribute to the broader ecosystem. So addressing small farm challenges, as the logic would say, economy of scale. So larger farms will have an advantage when accessing this opportunity, because obviously MRV may be cheaper and economy of scale works. So it's but still in Europe, while a few farms manage a big proportion of land, the average farm size, especially in the south, is still very small. So there may be some compensation that we need to take into account when developing a fair system that's not only rewards those that have already kind of easier to manage farms. Then ensuring value for farmers. The system works if you have multiple actors playing together. You need the certification body, you need the project developers that bring the opportunity to the farmer, you need the MRV, the verification bodies. So it's like everyone has a role to play, but ultimately the farmers are those bearing the costs at the beginning when implementing the practices of the change. So it's important that they receive a fair amount of the finances that are moved through this mechanism. Obviously, similarly, there is a mechanism of we should take care of or look at how we manage the financial risk, because often, and as you probably know, carbon carbon projects, you make your prediction, but then the certificates, the actual credits, are generated only later on in the process when you demonstrate that the activity was performed and generated expected results. So basically, that means that the money will go towards the farmers sometime 2, 3, 4 years later after they have started the changes. So, or let's say, use the resources to have those changes. So it is they are exposed to a risk, perhaps broader than others, but at the same time, there are also risks in the fact that you may expect something to happen, so you pre-finance that thing as an institution that wants to offset its emission, and then that things doesn't happen, so you have to finance something that is not doesn't produce the expected results. So that's also a risk. And all those things needs to be taken into account, and systems must emerge to kind of take care of these, and we see this happening. As Emanuele has shown, there are obviously, I know this is clarifying differences between offsetting and insetting. This is also another big topic. The corporate world is still has to kind of understand and develop a concrete mechanism to manage its own carbon footprint, let's say. So, and how you allocate carbon throughout the value chain, it's an ongoing debate. And that also generates challenges and differences when compared to offsetting, which is basically, I pay for my carbon footprint for somebody else to do a opposite action. So there are differences, and this understand how to navigate and how this can be comparable. It's very important for the system to develop accordingly. The fifth issue on the baseline, as mentioned by Emanuele, it's very complicated. There are various initiatives working on this. Another element in this conversation is let's say, how to do not make early movers feel that they are penalized. Because obviously, if they have done the practices earlier on, they cannot be recipients of carbon credits, let's say, so that they may feel, okay, we have done the effort earlier on, and now others that weren't ready at the time are also being rewarded. It is a difficult issue, but it is something that we should look at. One of our strong points throughout the different focus group in Credible is obviously that there are bioclimatic contexts that creates different challenges and opportunities in terms of carbon removal. And so let's say, a unique approach and methodology for the whole European continent, it may not make sense. We need these regional differences needs to be taken into account, and methodologies and projects will need to kind of really focus on what makes sense in that specific context. And this is it's a very important element. And then there is the last point is the importance of strengthening policy coherence. There are a lot of overlapping policy at the moment, the CRCF, the soil monitoring law, the natural restoration regulation, and many others that touches on the soil, that touches on similar or trying to implement at the farming level similar beneficial practices, and how to navigate and how to resolve sometime overlaps, sometime incongruencies. It must be really the focus of the next year's especially from the policymaker, but also from the supporting ecosystem that can help them. And when we talk about policy coherence, it's both horizontal, the one I mentioned, how different policies, let's say European policies, overlaps or articulate, and vertical, meaning so a different level of policy level, European, national, regional. There are also conflicting or enabling elements that must be found. So this is really it would be one of the focus from the policymaker point of view in the coming years. And with this, I've finished an overview of what are the main challenges at the moment around the general concept of carbon farming. Here, some let's say access to information, everything we generate, our focus group generates, and also the recommendation from the summits are shared. We have a Zenodo channel, and you can find everything in there. We have also recently launched a platform similar to the soil community platform, but it's specifically for carbon farming. Although at the moment it's more like a container because it hasn't got a lot of content in it, but it's the Credible platform can be accessed. And especially now, to conclude, an invitation to register to the Carbon Farming Summit. Registration are now open, and we have received 275 contributions. We expect sometime next week to give the results, to communicate to the contributors if they were selected. We tried our best to have everyone involved, but obviously 275 are a lot, and we had to also make a decision on certain occasion. But hopefully by the end of next week, if you have submitted the contribution, you would know. But I invite you to register nonetheless, because we have 750 tickets on sale, and we expect those to also go quite quickly. So thank you.
Okay, thank you very much, Tristano. So we are going to start the questions and answers section. Even though we are running out of time, I think we have to, because it's been a very intensive and interesting session. And there are some questions already on the chat. I know that some of you already answered, but I think that it's better if you also explain that to the audience, even though you replied, in case people didn't check. So there is a first one for Chiara, saying that given the low sites number, how confident are you that you represent the soil biodiversity in these 4 regions? Don't you think soil diversity is the first factor in terms of soil health? For Chiara?
Yeah, I mean, I in the chat. It's really relevant, but it was not the aim of the assessment we did. Because in the end, carbon farming projects are at the field/farm scale. So the assessment in this case is within the same type of soil. But I think one of the points made also by the authors of the OT-SOC index, for example, is that it would be good to test it on a wide variety of sites. So yeah, of course, I mean, it would be good to capture more soil diversity, but it wasn't the aim of what I presented.
Okay, thank you. So another question for Emanuele. Your modeling approach assumes that you somehow have soil type homogeneity at the plot scale, doesn't it? Also, shouldn't we assume that the MGMT practices will affect soil book density? Everybody seems to focus on soil organic carbon content evolution. That's only one part of the equation as far as SOC stocks are concerned. It seems to me that to assume that soil book density remains unchanged is a very strong hypothesis to make. Don't you agree?
Yeah, thank you for this question. It's open a very, let's say, a Pandora box. But so in general, from an experimental point of view, of course, it would be better to have the pile density to calculate by equivalent soil mass the soil organic carbon changes, of course. But you just to be aware that the certification of the price for the voluntary carbon market, the price of CO2 is about less than $10 for tons of CO2 equivalent. So this is more or less what you can sequester with the good management. So you get 20 euro, less than 10, 20 euros. And in the future is expected to probably grow to 50, and some prediction also say more. But with this amount of, with these prices, of course, you have to reach a compromise. And for instance, taking soil organic carbon, taking also pile density into, let's say, some carbon farming project can be really costly. Moreover, the certification anyway assure that there is additionality in your activity, that let's say you do something that is not business as usual. So you get to do different practices, that these practices bring co-benefit, and also that there is some sustainable requirement. So although, let's say, somewhat the certification pay the credits, and we try to estimate in the best cost-effective way, I would say is not 100% carbon center, because there is some rule related to the additionality to the co-benefit that somewhat assure that there is also a kind of transition toward more resilient ecosystems, and let's say, and of course accepting that we can have some if you want some let's say estimations, or some let's say approximation in the estimation of the carbon, which are really small changes. From a modeling point of view, then up to now it is very difficult to insert in the process model also the change in the structure. Basically, none of the models that are used commonly, the most, let's say, most used biogeochemical models, are not including the changes of structure related to different management. This will be too much complicated, and to this physics mechanism that will probably, for the moment, add too much uncertainty to the general, even the model structure. So they are parameterized to take into account probably the other main factor, like difference in input, different also in the nitrogen, different water content, but not in the model structure.
Okay, thank you, Emanuele. And another question for Emanuele and Chiara both. So in general, results-based versus action-based incentive, if we want not only short-term improvement in zero organic carbon, but also long-term storage, then maybe the move towards only results-based payments is not so useful. This way, farmers that are already doing good are disincentivized. So what are the thoughts about this on the level of EU regulation? If there are no possibility to calculate a maximum soil organic carbon per soil and pay a farmer more depending on SOC to max soil organic carbon for his soil?
Yeah, if I take that's also a very interesting question, and of course the CAP is is the first, probably, the common agricultural policy, action-based policy, and we see, you can judge if that's some benefit or not. For the voluntary carbon market, as I said, the idea is anyway to have some tangible credits that are related to emission removal, and so they can also be somewhat trade. And but as I said before, the law introduced this kind of co-benefits aspect and sustainability criteria that goes beyond a bit the simple carbon market, and the idea is that the farmer could renew certification in times and so what to bring the system toward a more resilience, a more sustainability. This is the main idea of the expectation. But of course, with the credits you can generate, of course, on inequality, because some soils maybe they are already depleted or in certain conditions they are more favored to accumulate carbon than the others. That's the point. Yeah.
Okay, Chiara, you want to add something?
If I may add, yeah, and maybe Emanuele, you can say if I misunderstood it, but because it's not only about carbon removals, it's also about soil emission reductions, right? So
yeah,
if you avoid losing carbon, that can also be rewarded. So if you start with a high level of soil organic carbon, you can still do something. And then the other point for me is that indeed this is a voluntary market, and maybe it is a good way to improve the soils that are really need to be improved. So maybe it's also okay that that it targets more soils that have poor soil organic carbon content at the moment.
Okay, thank you. So next question for Bertrand. Why is the effect of A, B, and C multiplied rather than summed up? Have you considered other models?
So yeah, to answer this, for the specific exercise, we do not consider any other models. We run it only with ROTC. In the MRV4SOC, we're using other models like the Sentry model, like the YASU model, and so on. Then for the rate modifier, it's based on the original equation. The idea behind is that you have a decomposition rate parameter, which is supposed to be like the optimum decomposition rate. So in what the conditions are optimum, and then those rate modifiers, they goes from 0 to 1. With 1, when it's a function, when it's 1, it means that, let's say, the temperature is optimum for decomposition. So the rate modifier related to temperature will give you 1. If it's really too cold or really too hot, then your rate modifier will reach values that goes towards 0. And so the idea is that you all those effects are multiplying each other's. So that's the way the model is built.
Okay, and another question for you. What about interaction between uncertainties like precipitation and clay?
So one of the reasons to choose ROTC for this study was that ROTC is a linear model. So it makes the decomposition of uncertainty much more easier. So we do not have such interaction in uncertainties. We tested it. The sum of all the interactions are always just few % of the total. So we consider them as negligible in this study.
Okay, so there are no more questions. I don't know if there is some last question or someone who wants to intervene, say something. You can raise a hand. No?
Okay, if there's no last questions, I just want to quickly touch upon a subject, if that's okay. I'm sharing a link on the chat. For those that are still present with us, I want to give an open call. We're starting also the webinars for next year, and we're looking for a wide variety of topics. So on soil biodiversity, on soil organisms, more on the policy side, or even case studies throughout your projects or anything that you'd like to share. It doesn't necessarily need to be related to a soil project. So if that is of interest to anyone present here, please feel free to contact me or with the link that I put in the chat. And yes, or scan the QR code. I just wanted to say that really briefly before your closing words.
Okay, so we can conclude this interesting and needed webinar about the carbon farming. We have seen that there have been identified different practices like cover crop with Poaceae, Fabaceae, and mostly as main families, or no tillage, that also increasing the development of mycorrhiza important for carbon sequestration. That organic carbon is characterized by high variability, and there is a need for cost-effective MRVs, so new models are needed with data assimilation, introducing biogeochemical processes and free available for users. There have been recommendations, suggestions of soil health indicator for assessing the improvements in soil health, but regional benchmarks are still needed for effective implementation. Also, we've seen the contribution for uncertainties in some models, mostly precipitation and clay, and process-based models can be an option to upscale from science to lab scale, but high quality of data is essential, is vital for this process. And also the carbon farming must also provide social and environmental benefits with the needs to address small farm challenges and regional differentiation. So more or less, this is some key messages to take home. And with this, we can conclude this webinar. Thank you for your participation. And I hope we can see you in next session. We will inform you about the topic. Thank you. Thank you very much for the speakers, for the high quality of the speeches and the contents, and for the attendees. Thank you very much.
Yes, thank you very much to the speakers. Goodbye, everyone.
Thank you. Bye-bye.
Thank you. Bye. Bye.